I'm a father. I'm a proud father of a 16-year-old. Actually, 17. She just turned 17-year-old daughter. She has one childhood memory which is stands out. It's one that she mentions every Christmas. It's about a Christmas in Copenhagen where we live, um, where there was enough snow for her to build a Christmas hut or igloo, if you want, for for her and I. Right, so we built it. It was brief because a couple of days later it was all melted away. But she remembers it very vividly, and whenever we talk about it, we will soon with Christmas time. So her eyes sort of light up. I recall building. I'm older, of course. I recall building a lot of igloos, whatever you want to call it, snow huts, castles, whatever we built with snow in Copenhagen when I was younger, like 30, maybe 40 years ago. Um, so there's no doubt about climate changes here. You've seen it in the news just lately within Spain and Florida and wherever. And that's why you are attending this session. I'm assuming you're all at least a little bit passionate about what you can do, what changes you can do. And that's what brings me why I'm standing here on the stage, talking about some of the stuff I've been part of doing and how you can replicate it. You're more than welcome to ask questions during the session as much as you want to. There's a lot of things we can dive deeper into or discuss if needed. I'm Anders, or Anders in American. I work at Microsoft. It doesn't really matter. I don't sell anything. I don't care if you use Azure or whatever. I just know a lot about those products. So things are built on Azure when we talk about this. We can get into a little bit of detail. The story is about Vestas. Vestas is they're actually called Vestas wind turbines because they produce wind turbines. It's the largest turbine manufacturer in the world, but that's not really interesting. The interesting part is that it's the most sustainable company in the world also, and they want to stay that way. They design turbines like this one. This one is actually called a V236. Now I know a little bit about what they're doing, and it's not the largest in the world right now, but it's huge. I've seen one of them. Each of these produce around enough electricity to power 20,000 homes. So it's big. And just to give you a little bit of idea of the scale, this is a single blade. There's 3 of them on a turbine. This one is 112 meters. At normal operation, these wingtips travel at a speed higher than any race car. And they need to do that for 30 to 35 years before you replace them. It's a huge engineering challenge. In fact, a little fun story when I met them, because we got to talk about things that are interesting. So I asked them, what's the ideal RPM of a turbine rotor? And they said, and there was one of the engineers, he was very calm, and he said, yeah, we can't really go above 15 RPMs, revolutions per minute, because then we'll break the sound barrier. Interesting, but I like these photos because they're insane. This is called a housing or nacelle. This is where the generator is located, and a lot of servers and all the stuff inside these. But the project we built is about wind turbine simulation. So we simulated that large turbine in all kinds of weird situations. So we need to simulate the load on the individual components, like the tower or a bolt or whatever it is. We needed to simulate optimal placement in wind farm. So if you place multiple turbines next to each other, you don't want one to sort of create wind shades for another, or as little as possible. And then also structural optimizations. So that turbine there, if you place that in, let's say, the North Sea, where there's a lot of wind gusts and seawater and all that stuff, compared to you place it, I don't know, somewhere in Central Europe, inland, there isn't that much wind gusts or anything like that. So the turbine can be different. There's a lot of material reduction. In fact, they can save up to 50 tons of steel on a single turbine. This is amazing numbers. Another number. The nacelle with everything in it weighs 880 tons, and they need to lift that up to 150 meters. Enough about turbines. Let's talk about technology. Of course, there was a lot of features we needed to build into this compute cluster that we need to create. So it's called a supercomputer, or more It sounds fancy with a supercomputer, but it's basically an HPC cluster, high performance compute cluster. And they had some requirements around this high performance compute cluster. First of all, they want it to be as cheap as possible. They want to make as much money as they want to, but they also wanted to scale to 400,000 cores. And that's an insane amount of cores. We realized that we needed, I can't remember, 6.5 million IOPS per second to sort of process everything we wanted, which is insane amount of IOPS. And of course, being the most sustainable company in the world, they didn't want to pollute more than necessary. Like, we really had to push all the buttons and levers we had to make it as green as possible. And this is super interesting because our industry emits more carbon than the aviation industry, and everybody's carbon shaming airlines and us traveling from A to B with planes. But in fact, we emit almost twice as much as the airline industry, which is insane. It's insane numbers. But nobody's talking about it, right? And it's not only these supercomputers which runs AI today, but it's pre-AI these numbers. So I guess it's not a great story. So I hope you're thinking, okay, cool. What can I do? I'm a software engineer. And not much, but you can. There's actually a lot of things you can do. But there's a lot of things you can do. So we worked heavily with Green Software Foundation. Actually, Microsoft is part of it. I am part of it. Green Software Foundation. It's free to be a member. You can join in if you want to be. They have a lot of resources, and they have these principles of making software greener and how you can do that. You can, of course, make your software more efficient. How do you do that? You can optimize your for loop. Probably not going to help much. You can change your programming language. I used to have a slide here that says Python is extremely slow, just to irritate Python developers, because I'm not. If Python is slow, but it doesn't really matter. Yes, if you run it on 400,000 cores, I wouldn't run continuously for years. I wouldn't run Python. I would pick something else. But in the software engineering, it's all about optimizing for developers and optimizing for delivery. So choose Python if that's what you want. You can look at other aspects. Then there is a hardware efficiency, like choose the right CPU SKU. The workload actually is super interesting. It has to match what you're doing. It's not, yes, we have general purpose CPUs, but suddenly we also have GPUs and other kinds of RFPGAs or whatever they're called. They are optimized for certain workloads and are a lot more efficient. You can don't have to buy the biggest server. You can just buy a smaller one that just fits the load. You can turn off unused resources. Cloud providers, again, sorry, I have to mention Microsoft a little bit because that's where I work. They have tools that sort of guide you, saying, okay, your server is 80% idle all the time. Why don't you pick a smaller one? It's weird that they do it because they make less money, but that is actually part of the portal today, if people are listening. Oh yeah, hardware efficient. We also saw at the keynote today, ARM processors, like Intel-based processors, have to carry a lot of weight. And most programming languages can run on ARM. I'm on a MacBook here, for instance. And if you bring up a laptop, a Windows laptop next to it, except the Qualcomm, they just released, the battery lasts a lot longer here than it does on Windows because it doesn't run in Intel. This is an ARM processor. And then there's going to be, we're going to talk a lot more about carbon awareness, and that's about, for instance, shifting when you do processing or where and stuff like that. There's a lot of things we can dive into there. Oh, I forgot to remove that one. That was the comparison of the programming languages. So, cool. So what do we do in this project? We first figure out how we need to make sure that no matter what we do, the most costly, meaning both in finance, meaning the piggyback out there, and the in carbon emissions, we need to make sure as slow as possible. So we need to figure out how to saturate these CPUs, making sure there was enough IOPS, because disks are generally not as carbon polluting, I would say. So we did that. Like, that was an exercise. We basically ran the same workload on many different types and figured out this is the ideal one. Then we right-sized the hardware, like made sure If you only need 4 gigs of RAM, don't install 8 gigabytes. It's stuff like that. Again, that saves money and it saves CPU. It's a fairly simple and trivial task to do. And then we scale up and down. Like we needed to go to 400,000 cores, but we could scale all the way down to 0. Like again, Christmas is coming. You see that in the stores. But during Christmas, nobody's working, at least not in Denmark, at least. And we don't want to have 400,000 cores sitting there just idling. So we could scale it all the way down to 0 cores, and that, of course, saves a lot of money, and again, carbon. And then using unused virtual machines, HPC is based on virtual machine, but we also used a lot of serverless functions. We'll see that later. So in all the cloud providers have something called reserved instances or spot instances. I can't remember what they're called in AWS right now. But in Azure, it's called spot instances. Basically means that somebody, a large customer, I don't know, Total Energies reserved 50,000 cores, but they're not using them right now. And then when they're not used, Microsoft resells them to others, for instance, Vestas, at a huge discount, often up to 90% discount. Right? So that saved Vestas a lot of money, and it also saved carbon because Microsoft didn't have to go out and purchase additional 50,000 cores. The caveat here is that whenever Total Energies figures out now we need to run our workloads with 50,000 cores, they want them right away. So you only have 30 seconds to save your work, and then the compute is taken away from you. I see this being used a lot, and then actually most people look at it as a cost-saving exercise, but it's also a huge carbon optimization exercise. So, carbon awareness. Let's drill into that a little bit. So carbon is CO2, carbon dioxide, right? But when I say carbon or CO2 in a sentence and we talk about sustainability, I actually mean another thing. I mean carbon dioxide equivalents. Right? And carbon dioxide equivalents because there's multiple gases that emit carbon. For instance, methane. Methane has a, what's that called? Global warming potential of 25, meaning it's 25 times more damaging or potent to the ozone layer. And then we have nitrous oxide, which is has a global warming potential of 298. These are huge numbers. We also need to know the term carbon intensity. Carbon intensity is the amount of carbon used to produce a kilowatt of hours. So we can write it like this. Carbon equivalents, carbon dioxide equivalents per kilowatt hour. This is a measurement you keep using when talking about carbon software or carbon production in all broad terms. For instance, to produce a kilowatt of hour electricity, if you use coal, you emit more than 1,000 grams of carbon. If you produce solar, it's between 22 and 46, depending on what kind of technology you're using. Hydro is 4, nuclear is about 16, and wind offshore is around 12 grams per kilowatt. So there's a huge difference what kind of electricity you're using. And that's why the next term here is electricity mix. So electricity mix is about, out of that socket in the wall, what kind of electricity comes out in your region? Lithuania, for instance, or Denmark. Like in Denmark, we have a lot of wind. We get a lot of nuclear from Sweden and hydro. We don't have any. We have a few gas plants. I don't think we have any coal plants left. But there's a carbon intensity of that region, and it might be different to the region next to it, depending on where do you get your electricity from today. And if you look at the electricity mix worldwide, the story is quite good. You see the renewables growing, and this is an old chart. I couldn't find any newer, but it's growing and it looks good. The coal is going down and renewables going up, and the trend is more extreme than it looks on this graph today. But then there's another graph. It doesn't really matter if it's not up to date, but there's another graph that just shows the amount of electricity we consume. It's not EVs. EVs don't consume much, but it's more production, like steel factories and stuff that goes away from gas, and it suddenly uses electricity. So from 85 to 21, for instance, we more than doubled the electricity production. In the next 5 years, where we currently are now, we need to double it again. So these are huge numbers that sort of have an effect on us. And we can utilize this knowledge that over time you can sort of the carbon intensity change. Like at this point, there's a lot of solar and wind, green technologies. But to fulfill the demand, which is this dotted line in the top, you need to use some coal and gas, for instance. And that might yield 120 grams of carbon intensity, meaning 120 grams of CO2 per kilowatt hour. Then a little bit later, I don't know, in the night or it was less windy, if the demand is the same, you need to fill that gap somehow. Like you don't have enough renewable, hence more gas and coal, and then you end up at 350, for instance. Why not utilize that? Because it jumps up and down all day long. So if that's the red one is the curve over time. If you have a workload you can move, for instance, batch-oriented, which HPC is, why not just move it over here? Like move your backup over here, move your batch processing over here. It doesn't have to be every evening at 10. For instance, there are other times you can run this. It's super easy. There's actually tools. For instance, the Akita controller to Kubernetes does this for you. You just set it up, saying, "Okay, I want the carbon intensity to be the lowest in the next 24 hours," and then it'll run your jobs at that point. A tool you can use, for instance, which we use. There's multiple of them. This is called electricity map that sort of shows the world of it, and this is a snapshot of how the electricity is at this current region. Of course, we have Lithuania over here. The color shows a little bit how green it is. I've picked two regions for a reason. I picked the Netherlands and South Central, and the Netherlands is here. And that's because Azure Data Center West Europe is located there. And in Sweden Central, near Stockholm, there's one called Sweden Central. So these are two Azure regions where we have large data centers. And you can see the electricity mix. You can actually dive deeper into it if you want to, but you can see in Sweden, for instance, there's a lot of renewables, wind, hydro, and solar, and the rest is probably nuclear. Where in the Netherlands, there's also a lot of wind and solar, not much hydro. It's flat as Denmark, but the rest is probably coal or gas, probably gas powered consumption. So if you want to go to that, let's try to go to that side right away. So, oops, that was me. Just need to find my mouth here. This is live data, and then you can actually, for instance, you can zoom into Lithuania over here on the side, and that was unfortunate. But normally we'll show you what the composition is right now, and you can see it over time at the carbon intensity change. So it's been quite high, and now it's dropped quite a lot. I don't know. You can get your dryer at home or washing machine to sort of say, okay, start when it's low, and you can actually these numbers also you can get predicted numbers, which in the next 24 hours is fairly accurate. But so these are some of the things you could do. Oh, that's not the one. Just give me a sec. Two hands is required. Why can't I get this one to close now? Oh, that's good. So we utilize that quite heavily. So we already done these things, and then we did time shifting. Moving from one region to another. Actually, we had multiple regions, but during our test, we only had these two regions, meaning Western Europe and Sweden Central. So we moved those. Moving a workload from one region to another doesn't really incur cost in Azure. It might incur cost for others, but in Azure it does not. The price. Sorry. Let me start with the time shifting. I was talking about location shifting. Time shifting, moving it to later in a day doesn't really incur cost. The service still costs $2 an hour, whether or not it's in the morning or in the evening. Location shifting, however, might incur a little bit of cost because The pricing is different in each region. It has to do with VAT, has to do with electricity prices and all that stuff. So there might be a little bit of cost incurred with that. So let's dig a little bit deeper into how we did this, meaning we coordinated a lot of data, because moving data is also costly, and you might not be able to do it. We could, and we also needed to coordinate time. So this is an architecture overview of the solution, hand-drawn, and there was a little bit more into this solution, but I'll try to remove most of what's not relevant. So if you look here on, I need to point over, no, it doesn't. I'll point on my hand then. The data center client, everything over here on the left is on-premise. Users using what's DC client, and everything on the right here is in the cloud, Azure. And then there's some interesting parts up here. And these, I don't know, cherries. It looks a little bit like cherries. You see, it says Sweden and Western Europe. These are HPC clusters. There's actually multiple of them. That's why there are multiple cherries. They are located either in Sweden or in the Netherlands, Western Europe. So, and then there's a lot of components in here that maybe we used, right? So we replaced an existing system, hence we knew the API already, and the DC client they already had. So when they submitted a job here, the executable, whatever that was, the parameters and the data was sort of shot off to an artifact storage, file share, nothing fancy. And then it was a message which was submitted to the API. The API didn't do much, it validated that files were there, that's it, and then it sort of send off a message to a queue saying, oh, we got a job we need to process. And it needs to be done by tomorrow at 8, something like that. Then we updated the state store. I'll just scan the state store down here. Then we had the dispatcher, and you can see there's some icons here. This is an Azure function, meaning a Lambda in the AWS world. A serverless function that's sort of been triggered by the messages arriving. And when we received that message, it sort of looked at that message saying, cool, I need to do a lot of things. First of all, I need to figure out how many executables are there. Figure out how long will it take sort of to process this job. Is it an hour? Is it 10,000 hours? Is it 100,000 hours? We don't know. But it can actually sort of look at that job and get an idea of how large the scope of this job was. Then it asks the APIs, the CO2 API in the top saying, okay, cool, we need to run this. When? Where? And once we decided that, based on carbon and pricing for that matter also, we sort of made a decision, okay, cool, we're going to run it in Sweden because there's availability of compute, it has an okay price, and the carbon is way lower than in Netherlands and West Europe. So we started copying the files over there because the file is needed locally. We don't want them to fetch a file somewhere along the way. Not 1,000 processes fetching the same files all the time. So we just copy it once. So that might be 50 megs we needed to move over there. No more than 50 megs. If we couldn't find a suitable location, we'll just put it back to the queue. Or, for instance, the user said, yeah, doesn't matter. Tomorrow morning at 8, that's fine. Okay, we won't start it now. We just put it back to a queue with a timestamp saying we'll start at 4 a.m. and then it'll be done at 8 a.m. for instance. So that's what we did. Whenever these jobs often produce quite a lot of output, some files and stuff like that, so we had to copy that back. That incurred, of course, some cost and some carbon. But we do that with we had a storage account here. Whenever a new file ended up in the out folder, it was called out, and that was when the processing was done. We started copying. We did that with something called event grid or cloud events. Whenever each file arrived, we just start copying. Again, we use something we called it blob trigger. Again, an Azure function, and we had some of the jobs we had. I don't know, close to 1 million files it needs to copy. But every time a file arrived, we just started copying it over there. And that's the beauty of the cloud. We didn't really care because that would just scale, and we only pay per I/O and execution. So whether or not we execute 1 at a time or 1 million at a time doesn't really matter. Right? That's Microsoft's problem. So interesting things about this solution is that intraday delaying of jobs, meaning time shifting, produced a 12 to 16% reduction in carbon. Moving a workload to another location, for instance, Western Europe to Sweden Central, because the electricity was greener, incurred a cost reduction in carbon between 30 to 90%. I'm aware that not all workloads can move around, but then you can just make a sane choice in the beginning. Can I have my, I don't know, servers, my compute replaced in Sweden Central? Why would I place it in Western Europe today? If the cost is comparable and I can save at least 30% carbon. So that's the easy solution. The takeaway from you guys, like, look at where do you want to run it? Like, yeah, go ahead.
If you move well to Sweden and you're using it won't the sun won't shine more and the wind won't start blowing more.
No,
where do you get the extra energy from? Hydro, but
yeah.
Otherwise it's coal or.
So the question was whether or not, because of the online folks, whether or not if everybody moves to the workload to Sweden and stop using Amsterdam, for instance, then you need a lot more power. Where does that come from, right? That has to come from, and I'm not saying Microsoft's doing it exactly as I think they should, from Microsoft pressuring Vattenfall, which that's an electricity company in Sweden, saying we need more X, Y, and Z green electricity production. We're actually doing that a little bit. It's not on my slides, but 74% right now in Sweden, that was a slide from a year ago, has what's called hourly matching, meaning the carbon consumed by the Microsoft data center was produced by green sources, meaning hydro, solar, or wind. That's still not good enough. And again, if Microsoft data center in Sweden is probably the fastest growing, I don't know, but it's growing rapidly, partly due to this. It's probably doubling in size every year at least. That requires Microsoft to invest in turbines, and they should, and they are, but not in the rate I think they should be doing. But it's not only a Microsoft problem; it's a general problem, right? But yeah, you're right. It requires more electricity of the right kind, not coal. And we can't just magically get more hydro, right? We're not going to get more rivers. So it's something else, right? So getting back to the tools we used, we worked again with the Green Software Foundation. We actually contributed quite a bit to them. We created a tool for this solution, so everybody else can use it. Actually, it's been used by Microsoft internally, and I know at least 30 other companies. But Green Software Foundation, and when we're talking about improving something, we need to be able to measure it, right? Otherwise, it's doing like this. You don't really know. So that's what we had. So let's figure out one of the tools here. So Green Software Foundation came up with something called Software Carbon Intensity Specification, but now it's a calculation I'm doing here on the screen. And just to get that down a little bit to understand, I'm just taking a random example, a fairly popular server called Dell PowerEdge, 3 gigahertz processor and 16 gigs of RAM. That's a normal server, I would say. So how do we calculate the carbon emissions of this server for a single hour? All right. We know we can look up the specs or measure it, that it uses 400 watts of power. That's 0.4 kilowatts per power. You can ask Dell what's called embodied carbon of the server. And embodied carbon is the amount of carbon it requires to produce it. I mean, each of the components, ship them to a factory in China or wherever they build it, ship it back to Sweden Central, and then also when you decommission it, like take it apart, and when you reuse parts, hopefully most of it. So that's the embodied carbon, and that's with the assumption that the server has let's say a 4-year lifespan, and then we'll switch out for another one. So 1,000 kilos, blah blah blah, calculation gives us 28 grams of carbon per hour, right? And then the grid we are operating in right now, in this example, the electricity mix is certain, so that's 216 grams of carbon per electricity kilowatt produced. And then we come up with something interesting here in the middle. This is called a functional unit, but we need to have something to measure it against, like how efficient is the system. And now this is, let's say, a web ordering processing system. So we processed 398 orders in that hour. Like, if it was idle, then the calculation would be terrible. And we do not include cooling or networking or anything like that. Which is, by the way, super interesting. If you look at old data centers, more than half of the electricity used was stuff like that, not powering. Today, it is super optimized data centers, cloud, for instance, data centers, they are at around 10, 12, 14% of it being used for other stuff of the carbon emissions. So they are getting a lot more efficient. But those are only the new data centers, not as soon as they are like 10 years old, changes. So we look at the formula. It's software carbon intensity. It's built up of a couple of things here. There is the energy consumed by the software, 400 kilowatts. There is the carbon emitted by the energy, the carbon intensity. There is the embodied carbon, producing the server, decommissioning and all that stuff, and then the functional unit, right? That's where I had the orders. And if we do like this, we have magic. We got all the numbers. Then we sort of put them into the formula. We use some animations. So 0.4 times 216 yields 86 grams of operational carbon emissions, meaning running the server. And then we include the server provisioning and decommissioning, and then it ends up with 140 grams. And then we need this functional unit to sort of figure out what does that yield per order, 0.31 grams, which isn't much. I drive a 11-year-old Ford Fiesta, 1.0 EcoBoost, and per kilometer it emits 140 grams. So this isn't much, but still, if you process a lot of orders like Zalando, that adds up quite quickly. So I really like this formula. It looks a little bit scary when I first saw it, but it's super simple because it's easy to understand, and each of these values sort of make sense. Like you have the energy consumed, so if you make your software more efficient, let's say shift to an ARM processor, the E will go down. If you pick an electricity source that's more green, or I don't know, we plug in a solar panel directly, your I will go down. If you extend the lifetime of a server or pick a more green provider, a sustainable provider, your M will go down. Or if you, I don't know, force customers to order more or whatever, figuring out how you can change your functional unit so it's more increased, then that will go up and the number will go down. So there's a number of additional tools you can use for this. So the carbon aware SDK is what we built and committed back to Clean Software Foundation. And it sort of gives you these nice endpoints, like saying I have a workload and now it's going to take me an hour to process. Where should I look? When should I do that within the next 24 hours? And you can also step it up further and say, okay, I have an hour worth of processing. Where? And that's an addition we also made. So these are the APIs. About a year ago, there's a few new arrived also, but you can also get forecasts and stuff for other things that these carbon intensity providers delivers. Yeah, let me just do like this. So Vestas went a step further for us and challenged us on this, right? Because it's not only about finding the most green location, because they gave us this challenge that they don't mind to stay the most sustainable company in the world by paying 5% extra for a large reduction in carbon. But the vice versa statement is not true. They cannot afford to pay a lot more for almost no reduction, right? And if you just look at the carbon data and say, okay, I want to run it here and move it to this location, and if it's twice as expensive, that's a problem, right? Imagine the scenario that we had very polluting, well, not very green data center in Western Europe, but spot instances available. Like we got a 90% discount on compute. The alternative is to cut the carbon emissions by 90%, move it to Sweden, but there's no spot instances, so you have to pay regular price. They don't want to do that, or they could set it up in the system, but I wouldn't pay 400% extra for it, and neither would they. So that's kind of the challenge we had. So we solved that a little bit by, you remember the dispatcher, by something we call the carbon economy SDK. So you remember the dispatcher, which called out, I was vague in my terminology earlier when we saw this a little more advanced diagram, but it calls out to what the carbon economy SDK, which is public available also, which called out to Azure pricing API, got what's the current price? What can we get it for? Can we get a spot instance with 9% discount? Yes, you can. Cool. And then we called out the carbonware SDK, which eventually called out electricity maps, and we got the data back. And then we sort of had to evaluate, what are we doing right now? Are we willing to pay 10% extra for a large reduction, or is there almost no reduction? Then we'll take the cheapest place no matter what. The carbon economy is also public available and easy, free to use. The only challenge is we're trying to get it into Green Software Foundation. The only challenge is it's only working towards Azure, and that's not good enough for them. But it will end up there eventually, but it's available. And the way I did it was a normalized formula with a weight. Not gonna, yeah, now you know. Just giving you an example here. So you see, if we had, for instance, 4 data centers: Sweden Central, Norway East, Western Europe, South, UK South, with an it says emission rating, but carbon intensity, and a unit price of whatever it is we need. And then up here we have an emission weight. So emission is not super important. And then we do the calculation, then we realize via the formula before that we need to end up in West Europe. If we change the weight within exactly the same numbers, just a little bit, we end up in Norway East in this example. So we actually spent quite a bit of time on figuring out how the hell do we do this weighting thing. First of all, there's a UI challenge. I'll show you that in a second. Second of all, it was, I think we spent a couple of weeks just on diving down, and we came up with more and more advanced formula. But we ended up with this fairly simple one. We didn't see any value in creating a more advanced one. And this is actually the UI, the admin UI for the wind turbine simulator. And there's a lot of settings down here. When do we consider it a good discount? Something about what's the carbon emissions over the last period of time. Trying to nudge the users a little bit. These are the admin users. How long the execution time was. Again, knobs they can control a little bit with cost. But the most interesting part was this part up here in the top right-hand corner. Is you see these leaves and these dollar bills. And that's how we set the emission weight. So there's 25 times 5 times 2, 5 times 5 gives 25 settings. You can actually set. So we had pre-configured settings depending on where you set that. These slide bars, and then we sort of nudged the user a little bit, saying over the last 30 days, if you move that slider just a tad to the right, you would save 5 metric tons of carbon dioxide. But we also did another thing just for the fun of it, or UI designer did. So depending on how you set the settings, we sort of make these turbine, instead of being in a lush forest, it sort of ends up being a cesspool, right? So we had 25 different images for that, just to nudge them a little bit. Yeah. Then, yeah, a little bit about, I'm working internally at Microsoft, and I work with our competitors also in a collaboration to get a standardized way of getting this data out to you as users of cloud. and it's not an easy task. Microsoft came out with this about a year ago. It's called the Azure Carbon Optimizer. Terrible name. Yes, it can tell you you should scale down your VM because it's not it's too big compared to the workload you're running on it. But the most valuable part is you can actually get your carbon data out of it. It's a little bit delayed, 30 days delayed, which is unfortunate. Trying to get that down, but you can get your carbon emissions out here, and there's also an API where you can fetch all this data. And Ignite, believe it's next week. I can't really tell you what's coming, but it won't be a major announcement, but there's some really nice enhancements that makes it easier for you to take action. Like, so whenever you choose this version, this service over this service, you'll get a lot of information of which one should I pick. There's of course pricing, but there's also other aspects into this story, right? So this is what we're doing. Our Google and Oracle and the others, AWS, are doing something similar. I'm just going to jump through that. I hope you've been inspired. I hope you learned a little bit. I hope you're going to take something away from it. The simple thing you should, or the small things to take away here: pick a data center that's green. Whatever it is, doesn't have to be Microsoft. Probably ends up in Scandinavia somewhere, if it has to be in Europe, and if you can do that. Alternatively, you can go all the way in, where we did, like moving workloads back and forth. That was also another reason we had to do that, because you can't just get from 1 second to another 400,000 cores in Sweden Central. You might not. So we had this scale thing that we need to move things around. Interesting fact: the carbon emissions went significantly down for Vestas. They had an on-premise, and they were just planning on installing it in one location. We can see significant drop in just comparison both what they had on-premise and if they just used one location. But the icing on the cake is they're also saving money due to spot instances. So we managed to reduce their carbon emissions and save them money at the same time, which was not our intent. Not that I don't care, but they are happy, and so which makes me happy.